Next up on stage tonight, we have our change maker, Faezeh Pazoki, a Ph.D. student in the Department of Civil Engineering under the supervision of Professor Jinxia. Tonight, Faezeh is going to show us how clay can be the superhero in our lives by help removing forever chemicals from the environment.
Meet Timmy. He's a typical 5-year-old living in a small town. Just like any other kid his age, Timmy is full of energy, curiosity, and dreams of superheroes saving the day. But there is something not quite typical about him. His blood contains a very high concentration of a certain chemical. These chemicals are known as per and polyfluoroalkyl substances, or for short, PFAS. While it's never good to hear that you have a strange chemical in your blood, it's specifically concerning with PFAS because they've been linked to a long list of diseases like cancer, diabetes, infertility, and more. So what are these PFAS exactly, and how did they end up in his blood? PFAS are a group of synthetic compounds that were first introduced in the 1940s. Today, this group contains over 15,000 different compounds, and their main characteristic is their long carbon-fluorine bond chain. The carbon-fluorine bond in a PFAS molecule is the strongest organic bond, giving them the incredible stability and very high thermal resistance. But it doesn't end there. PFAS are hydrophobic and hydrophilic at the same time and can repel water and oil simultaneously. All these incredible features make them unique and irreplaceable in today's world. From your favorite non-stick cookware to the waterproof jacket to even food packaging and makeup, they all contain PFAS. But Timmy doesn't use this product any different than us. So how did he end up with such high levels of PFAS in his blood? The answer lies in a surprising source: firefighting foams. Firefighting foams are essential tools in modern world, but they also rely very heavily on PFAS. Because of its unique high thermal resistancy, they're ideal for these applications. Places like firefighting training sites, airports, and military sites use these foams extensively on a daily basis. Over the years, PFAS can leach from these foams to the soil and accumulate them. The very stability that I keep mentioning, the very strong carbon-fluorine bond, have come with an unintended consequence. These molecules do not break down in the environment. Once they're released to the environment, they're going to stay there forever. That's why we also call them forever chemicals. While some of the PFAS compounds are mobile and will move to the water bodies, some other are very soil-bound and can stay in the soil for thousands and thousands of years to come. They can act as an infinite source of water contamination. Unfortunately, this is exactly what happened near Timmy's town. A former military site used these foams extensively for many years and has resulted in PFAS accumulation in surrounding soil. PFAS has now leached into their drinking water, and they have been drinking the PFAS contaminated water. In Canada and almost everywhere else in the world, there is no drinking water regulation for most of the PFAS compounds found in firefighting foams. That's why the elevated levels of PFAS in their drinking water went unnoticed. So, what are our options? How should we stop this issue? Traditionally, when dealing with persistent organic pollutants, we have a few options. We can dig the contaminated soil, move it somewhere, store it safe. But the extent of contamination is too large for that to be a reliable option. We can also add very harsh chemicals to the soil and degrade all these contaminants on the spot. But they happen to be ineffective for PFAS, and also they usually have a very large environmental footprint and can harm the ecosystem. Lastly, we can clean the contaminated water, but as I mentioned, that only ends up to be a never-ending treatment process because of the amount of contamination that's out there. So, what are other options? Enters the hero of our story, clay minerals. Abundant, affordable, and very often underestimated, clays can be very useful. We've been using them for many, many years, from the ancient pottery to modern building blocks, but there are way more than that. This is how a clay mineral looks under a very strong microscope. They're made of thousands and thousands of tiny, tiny crystal layers. These crystal layers are mainly made from aluminium and silicon, but they sometimes have other materials in them as well. I am using an iron-containing clay mineral to solve this issue. In the lab, through some chemical processes, I reduce this iron to activate it. So once the clay is added to the environment, it becomes to the proximity of PFAS, but also oxygen. The iron inside the clay mineral reacts with the oxygen and produces something called hydroxy radicals. In chemistry, we call something a radical when it has an unpaired electron. These molecules are very strong oxidizing agents, meaning they're willing to do anything to pair that electron, to fill that gap. So in the environment, the hydroxy radicals are going to attack PFAS molecule. They're going to get their electron from the weaker bonds in a PFAS structure, and as a result, break that into smaller pieces. These fragments are now mobile and can be washed away from the soil. In the lab, I reduce the iron, I activate it through some chemical processes, but in the environment, there are some microorganisms that can do this for us. So once we add the clay to the environment, we don't really need to do anything. It can continue producing hydroxy radicals and activating the iron on a cycle, breaking all those PFAS compounds and leaving the soil clean. But I see some skeptical faces in the crowd. It looks like I made the situation even worse for Timmy. All these PFAS compounds were sitting in the soil, and I broke them and released them into the water. Well, you're right, but don't worry about it. Madam Clay has another solution in her pocket. This time, it's called sorption. I'm studying a specific clay that's commercially modified with a specific polymer inside its structure. The polymer has two jobs. One, it introduces some PFAS-specific sorption sites that acts like hooks and attach to a PFAS molecule. Two, it increases the distance between these layers just enough so that PFAS molecules can fit inside. So when we add these modified clays to the water, all these PFAS compounds are quickly sorbed and stuck inside these interlayers. Let's look at some of my results. We see that modified clay can remove 100% of PFAS from water in only a few days. To put this into context, modified clay is far superior than other popular sorbents in the market, like biochar and activated carbon, and it's very comparable with ion exchange resin, while being way cheaper than that. One very important factor to consider when we're talking about sorption in a real environmental condition is the presence of salts and organic matter and other co-contaminants. It never happens that we have water and our target compound. There's always something else in the environment. There are salts, as I mentioned, and other stuff. We see that the presence of co-contaminants significantly reduce the sorption efficiency of all these other sorbents, but does not affect the modified clay. This is because all these sorbents are surface sorbents, meaning there's a large surface with all those sorption sites available on them. Any compound that comes can go and grab a seat and stay there. But with modified clay, because of its layered structure, these sorption sites are reserved for PFAS inside the layers, and those co-contaminants, like organic matter, are often too big to enter those layers. My results show that none of the conditions tested have any significant effect on sorption efficiency of modified clay, even at very high concentrations. Knowing this, we can get columns, fill them with modified clay, and install them downstream of the contaminated sites. All those now mobile PFAS compounds are going to be captured with these columns before they can leach to the drinking water of Timmy and his community. Later on, we can get these PFAS-filled columns to the lab. Using our good old friend iron-containing clay mineral, we can now destroy PFAS to its building blocks of carbon dioxide and fluoride. Thanks to Madam Clay, Timmy is now safe, and without having to worry about contamination, he can grow up happily. This was Timmy's story, and yours might be intervened with it more than you know. A recent study showed that every single drinking water sample collected across Quebec has PFAS in it. That includes every single water sample collected in Montreal. Environment Canada reports that there are over 600 firefighting foam contamination sites all over the country and more than 6,000 PFAS contamination sites from different sources. A study shows that 98.5% of all Canadians tested have PFAS in their blood. While our fight against PFAS is far from over, innovative solutions like clay-based remediation offer a glimmer of hope. Unlike traditional methods that leave behind their own environmental footprint, clay has a cleaner approach. Its natural properties can be harnessed for remediation without future problems. This focus on sustainability is essential as we move forward. Prioritizing solutions that do not create future burdens is vital for building a healthier and more resilient future. Thank you.